Okay, so we'll start with this week's session. So this week basically covers week 5 topics regarding mobile robot localization and odometry. So again, like this week we'll be discussing some questions that has been that will probably that is intended to help you to solve questions that is from week 5 regarding mobile robot localization. Could help you in solving the assignments, or if you have already solved the assignments, in case if you have any doubts, or in case if you have any issues with the questions that is being asked in the assignments, you can raise it here during this session, or maybe you can see how the problem is being actually solved. It may help you uh, in solving the final exams as well, final certificate exams as well. So we'll proceed with the session. Yeah. So question 1 says, given a differential drive robot which localizes itself in a work environment using odometry based on the wheel sensor readings, select the deterministic errors that can be eliminated by proper calibration of the system. All right. So you have been given a differential drive robot that should be localizing itself in the work environment using odometry based on the wheel sensor readings. So basically, you would know that there are two different kinds of error. One would be deterministic errors, and the other would be non-deterministic errors. So as you would know, out of the two classification of errors, which are deterministic and non-deterministic errors, the deterministic errors can be eliminated by proper calibration of the system. So this can be eliminated by proper calibration. Whereas in the case of non-deterministic errors, these are also called as random errors or non-systematic errors. So random errors cannot be fully eliminated from a system. The only way we can accommodate such errors would be to make an appropriate error modeling of that errors, so that it can be incorporated into the system. We can have compensate for these errors as well using some error modeling. So the question says we need to select out of all the given options, A, B, C, D, E, I think 5 options are given, which one of them comes under deterministic errors. The errors that can be fully eliminated by properly calibrating the system. So what about the first option, limited resolution during integration? So is that a deterministic error or a non-deterministic error? So limited resolution during integration is basically a non-deterministic error. It cannot be fully determined. Because the integration would be mostly numerical, so it'll be based on a discrete number of steps. So even if we bring down the number of steps, or even if we bring down the size of steps to a very infinitesimal value, still there would be some errors, and that would basically propagate as we further integrate in higher orders. So that is basically a non-deterministic error. And what about uncertainty in wheel diameter? And in particular, unequal wheel diameters. So if this can be basically calibrated, we can basically make sure that both of these wheels are more or less identical using proper manufacturing techniques, or yeah, exactly. So this comes under deterministic error. And third option comes variation in contact points of wheel. So if you are talking about a differential wheel drive, and if you are designing a controller input in case of differential wheel drive, and suppose if you want the robot to move in a straight line, so what would we do? Suppose this is a differential wheel mobile robot, and if you want the robot to move along the x-axis, So we would give equal inputs in both of these wheels, F and F, so that the robot can move in a straight line. But due to the variation in contact points of wheel, like we cannot ensure both of these wheels will have equal traction uh, on all time. That cannot be actually ensured. So if that cannot be ensured, then would the robot be able to impart equal forces on the surface? It won't be able to impart. So again, like variation in contact point of the wheel, that is not basically in our control. Like no matter how hard we control or how hard we calibrate the system, it cannot be fully eliminated because it's based on other parameters also. It's not dependent on the system. It can come from the external environment also. So again, this class comes under non-deterministic error, as it cannot be fully eliminated through calibration of the system. And the misalignment of the wheels. So again, this is similar to the case of unequal wheel diameters. So misalignment of the wheels, again, we can tune the steering axis. If it is a steerable wheel, we can basically tune the steering axis of the wheel. Or if in case of a differential wheel, we can basically fix the mountings properly. We can calibrate the mountings. We can basically calibrate the mountings properly so that the misalignment can be eliminated. So again, this comes under deterministic errors. And for the fifth case, unequal floor contact. So unequal floor contact, that's also a similar case to variation in contact points of it. So like if we want the robot to move in a straight line, and if we would basically desire our desired forces should be uniform through both of these wheels. But due to unequal floor contact, like we cannot basically ensure the floor contact to be equal throughout, because floor is part of an environment, and we cannot basically make sure the environment could be so smooth such that the floor contact would be uniform throughout. That cannot be. We cannot, no matter how hard we calibrate, we cannot fully ensure that. So again, this also comes under non-deterministic. So in that regard, the question asks to identify deterministic errors. Deterministic errors are the errors that can be eliminated by proper calibration. And out of all the 5 options, the deterministic errors are misalignment of wheels and uncertainty in wheel diameters. These are the only 2 errors that we can somehow eliminate by proper calibration the system. So the correct option for this question would be, question number 1 would be options B and option C. Right. So if we check the answer key, according to the answer key, the correct options are options B and D, which are the deterministic errors. Option B and option D. These are deterministic. All right. So moving on to the next question. So it's a numerical question. It says a differential drive robot at the initial pose at A is given as 2, 3, 25. So the initial pose of a differential drive robot T is given as 2, 3, 25, where each of these values corresponds to x coordinate, y coordinate, and theta coordinate. Because for a differential drive robot, or rather for any robot, any mobile robot, surface mobile robots, it has 3 degrees of freedom. So you would require 3 degrees or 3 variables to fully define its configuration. And it also says that the robot moves to another point B, and the distance between 2 wheels is given as 1 unit. So if this is the differential wheel robot, so we have been given the wheel to wheel distance B as 1 units. So the question asks, given the distance between the two wheels is 1 unit and the right and left wheel traverse a distance, right and left wheel traverse distances are 3 and 2.5 units respectively. So yeah, the left wheel traverses 2.5 units and the right wheel traverses 3 units, delta SL and delta SR. So the absolute traverse distance of the robot is. So this is basically a straightforward numerical question. So it basically asks you to find out the absolute traverse distance of the robot. So if, yeah, since it basically says like the one of the wheels moves a traversing distance of 3 and the other wheel traverses a distance of 2.5. Then what would be the absolute traverse distance of the robot? If this is delta S, this is delta SR, if this is delta SL. So you can consider this to be two extreme edges of a trapezium. So if two of the extreme edges or two of these parallel sides are known, then what would be the length of the, what would be the height of this trapezium? That is what the question is. So basically, geometrically, it's basically the average of the length of the parallel sides. So delta S would be delta SL plus delta SR, the whole divided by 2. That would be 2.5 plus 3 by 2. Is it 2.5? Yeah. So the correct answer would be 3.25 by 2. Sorry, 5.25 by 2. That would be 2.75. So the distance the robot traverses would be the average or the mean of the distance traversed by the left wheel and the distance traversed by the right wheel. It's a fairly straightforward numerical question. So the correct option in this case would be option C, 2.75 units. Right. So moving on to the next question. So again, it is a continuation from the previous question. All the parameters, I'll reproduce it again. P would be 2, 3, 1 second. Yeah, 2, 3, and 25. Delta SL is 2.5. Delta SR is 3. And the wheel-to-wheel distance is 1 units. I'm again reproducing the chassis, the robot, differential robot. The wheel-to-wheel distance is given as 1 units. This would be the distance traversed by the right wheel. This would be the distance traversed by the left wheel. So the question asks, what will be the change of pose from point A to point B? So we have already determined the total distance traversed by the robot's center, or the center point would be delta S, be average of distance traversed by the right wheel and distance traversed by the left wheel. So this would be 2.5 plus 3 by 2. This would be 2.75. And if you can recall the formulas for the change of pose in x direction is simply delta S cos theta plus delta theta by 2. Delta Y would be delta S sine theta plus delta theta by 2. And delta theta would be the change of orientation. And again, what would be this change of orientation? Delta theta would be delta SR minus delta SL divided by 2 times the wheel-to-wheel distance. So again, just by substituting, it's a fairly straightforward substitution. Sorry, it'll be B actually. It's not 2B. Yeah. This would be 3 minus 2.5 by 1. It would be 0.5 units. So substituting delta theta back to find out delta x and delta y. That would be delta x would be 2.75 times cos theta would be this one, this value 25 plus delta theta 0.25. Delta y would be 2.75 cos, sorry, sin theta 25 plus delta theta by 2 and delta theta. This we have already found out to be 0.5 units. And if you substitute all the numerical values, you would end up with delta x to be 2.49 units. Delta y would be, I guess, 1.17 units. Right. So this would be your change of pose. The change of pose vector would be delta x, delta y, and delta theta. So accordingly, if you see the corresponding option would be option A. 2.49, 1.17, and 25 degrees. Sorry, I guess it's option D, right? Yeah. 2.49, 1.17, and 0.5. Yeah. If you take a look at the option, it's also 0.5. It's a simple, straightforward substitution into the equations. First, you find out delta theta. Then from delta theta, you will be able to find out delta x. Then from delta theta, again, you will be able to find out delta y as well. And again, moving on to question 4, it's also again a continuation of the previous problem. Yeah, Murali, do you want to say something?
Yeah, can I ask a clarification?
Sorry?
Can I ask a clarification?
Yeah.
So, we go to the previous question, number 3.
Yeah.
So, to get this change in pose from A to B.
Yeah.
So, in terms of units, what would these actually represent? 2.49, what?
Units, like in the question doesn't specify any units actually. It only says units. It could be anything, right? So delta, I think this is the original question. It only specifies units actually. So 3 and 2.5 could mean meters. It could mean anything in meters, millimeters, or anything. Units are basically units of length.
Yeah, I mean, for
Those are
X and
basically
Y,
units of length. And the theta's unit would be, it could be either degrees or radians. But judging by the question, I suppose it should be in degrees because it says 25. So that could be in degrees also.
okay.
Right?
Okay, thank you.
Okay. So just to check the consistency of the unit, delta theta here says, yeah, delta SL and delta SR by B. So again, numerator is also lengths unit, denominator is also lengths unit. So it basically cancels out. So you will basically, you will only remain with the radians or degrees. Yeah. And fourth question, again, a continuation of the previous question. It says, find the y coordinate of the new pose of the robot up to 2. It's a numerical question. So again, like you were already given y. Y was already given. So the original pose of the robot, as per the previous question, was 2, 3, and 25. This is original pose. And the new pose, the change in pose, we have already identified from the previous problem. That would be 3, 1.17, and 0.5. And what would be the new position of the robot? That would be the previous position plus the change of position, p plus delta. So if we add this up, we would end up with the vector. The absolute position, absolute final position of the robot would be 5, 4.17, and 25 plus 1, 25.5. So in this regard, the question specifically asks to find out the y component, the y coordinate. So this corresponds to the x coordinate, this corresponds to the y coordinate, this corresponds to the theta coordinate. So in this case, the correct answer would be 4.17 because the question only asks the y coordinate only, not the entire vector. Right? Yeah. Again, checking the question, it's in line with the formulas also as well. Okay, so moving on to question 5. This is a true statement. Choose the true statement. It could be multiple options, and or it could be a single option. So we'll go through these options one by one. So yeah, option A says prediction update is based on updated belief state. So is it true or false? Again, like I think it would be better if I give you a brief overview of what the belief states are. Belief states, all these terms are. So again, belief state is nothing but belief state. Should be the best guess of where the robot is currently. Best guess of robot's state. And like, if you have followed through the lectures, you might have noticed two different terms of beliefs. Like one is called a perception and the other is called a prediction. So the perception or the prediction basically deals with the belief state, belief bar xt, which is denoted as such. Belief bar xt or the prediction update would be the probability that the robot is at the current position, provided all the sensor readings up to the previous position 1 to t minus 1 and all the control inputs. Control inputs is defined as u from 1 to t. So this is prediction update. See, ideally, if we have a robotic system, a robot would be at time t minus 1, it would be at x t minus 1. And at time t, it would be at position xt. And the first stage would be, you would give a control input based on the odometry. Based on its odometric data, you would give a control input. The robot would move to a location, basically xt. So before measurement. So belief bar xt or the prediction update would be where the robot would end up just by having its odometry, just by having its control input. This is just before measurement. So in other words, belief bar xt is the position of the probability that the robot is at xt just before taking its observation, just before observations from the sensor. And again, like belief xt, the second one is probability that the robot is at xt given the sensor readings from 1 to the current time step and the control inputs from the first position to the current time step. So like earlier, like when the robot, just with the control input, robot moves from xt minus 1 to xt. So that is belief bar xt. Now, when the robot reaches xt, it will check with the sensor reading. It will basically checks with whatever readings it is getting from the sensor. So that is what we call perception. So where robot is currently compared with what the robot actually sees. That is the difference between perception and prediction. Right. And yeah. And option A says prediction update is based on updated belief state. And again, like how do you calculate prediction, the belief states actually? So the numerical value, the probability that the robot is at the current state prior to the measurement of the prior to obtaining the measurements from the sensors would be integral probability that the robot is at xt given the control inputs and given the prior information when the robot was at time t minus 1 times dx t minus 1. This is basically the probability distribution. So yeah, this is basically the probability the robot is at xt given the control input ut and the previous position update also. Previous position update actually. Previous position state. It's not update, previous position state. Yeah, this is prediction actually, prediction. And belief of xt would be some factor times probability that the robot sees at time t given the current position and the map times belief bar xt. So belief bar xt means the probability that the robot whatever the robot is seeing, whether it is seeing what it should be seeing, like it has its own map and the current position. So it basically estimates from the sensor whether it should, whatever it is seeing, and it compares with whatever it should be seeing from the map. So map corresponds to the objects, the features the robot should be seeing, and ZT would be whatever the robot is currently seeing from the sensor. And this is multiplied by the previous probability, the prediction update. This entire thing would be the perception. Right. So the first option says prediction update is based on updated belief state. So what would be the correct option? Prediction update is based on updated belief state. So as you can see over here, this is the prediction update. And in nowhere in this definition, you would see an updated belief state. It depends only on the previous state and the control input. Prediction update only deals with the control input and the previous state. Whereas if you look at the perception input depends on the current belief state. It depends on the current belief state, provided it has accurate estimation, accurate information regarding the map and its current position also. So in that regard, option A is not correct actually. It is not prediction, it is perception update that is based on updated belief state, not prediction. And what about the second option? Perception update decreases the uncertainty of the robot, decreases the uncertainty as the robot moves. So just with prediction alone, just with odometry alone, the uncertainties increases as time goes. Because due to the uncontrollable errors, due to random errors and all these things that cannot be uncontrolled, if some error gets into the system, it will get integrated and it will increase. If you bring the perception, if you bring sensor data, and if you compare with where the robot is and where the robot should be, using these comparisons, it can be brought down as the error can be brought down. the corrective measures can be chosen. So whether the statement perception update decreases the uncertainty of robot, decreases the uncertainty as the robot moves. That is correct. Because as the robot moves, it'll see what it should be seeing using its sensors. And perception is based on sensors actually. So that statement is correct. And option C, action update is based on prior belief state. Right? Action. So again, like action and prediction update. So action update is another name of prediction update. Prediction update is also called action update. It's just another name. It's just a different. So whether prediction update or action update is based on prior belief state. It's easy to get confused. It now says prior belief state. Again, action update is action and prediction are essentially the same thing. Action and prediction. And if you can see the definition of prediction update or action update, it indeed does deal with the prior belief state. This is the prior belief state. So the prediction update or action update deals with the prior belief state. So again, that option is also correct. And the final option, prediction updates increases uncertainty as the robot moves. So prediction update, it does not have current sensor data. It only has the sensor data up to the previous time step. It does not have current sensor. Prediction is right before the sensor makes any measurements. So in that regard, just with prediction update alone, it will increase the uncertainty. So again, that option is also correct. So the uncertainty is kept in check using the perception update. Prediction alone would only lead to the increase of uncertainty. So in that regard, options B, C, D are the true statements. Like, is there any conflict in this regard? I hope it is clear basically. Because these are basically covered in detail in the lectures. So it can be confusing because these terms are prediction and action are basically the same. And unless you are fully thorough with what the prediction update is and what the perception update is, it can easily be confusing. So I hope it's fine. I hope there is no conflict of interest in this question. Yeah, the correct options are B, C, and D. Okay. So moving on to question 6. It's a question regarding Markov localization. So the first option says only the current sensor measurements are required for accurate localization. Is that correct for Markov localization? Only the current sensor measurements are required for accurate localization. That is straight away false, because if when discussing Markov localization, it states that all the sensor measurements from the beginning of the time to the current time is required for accurate localization, for Markov localization. And the second statement says the current state is only dependent on the previous state and its most recent actions in perception. So current state is only dependent on the previous state and its most recent actions and perception. So that is correct. Because the current state is xt, previous state is xt minus 1. Most recent actions would be the control input ut, and the perception update would be belief xt. So that is correct actually. The current state, error modeling or the error propagation of the current state is dependent on all these parameters. Previous state, the control input, and the perception update also. Because the control input deals with the prediction update, belief bar, XT, and the sensor readings would come into the perception update. In that regard, option 2 is accurate. It's correct. And option 3 for question 6, the probability that the robot state estimate equals the actual robot state is maximized. So again, we are not dealing with any maximization function. Like, we are only keeping this error bound in check using perception update. And nowhere we have actually seen a use of a maximization problem or an optimization problem. So that, yeah, the robot's state estimates is basically at its maximum. So again, that is not a valid assumption for Markov localization. And it also says the Markov localization tracks the robot and is very inherently precise and efficient. So inherently precise and efficient cannot be associated with Markov localization. This can be associated with the Kalman filter localization. So again, that is not a given assumption or a given performance characteristic of Markov. It's only dependent on Kalman. So again, this is not a valid assumption or a valid criteria for Markov localization. Precise and efficiency are mostly associated with Kalman filters, not Markov localization. So in this regard, the only correct option in this regard would be option B. The current state is only dependent on the previous state and its most recent actions and perception. All the other options are not valid at all. So option B indeed is the right answer. So moving on to question 7, this is also a true or false statement. It says select the false statements. So going by option 1, so in Markov localization, to update the probability of all positions with the whole state space at any time requires a discrete representation of a space grid. So that is basically correct. So you would have to discretize this entire grid or the entire workspace of the robot into finite divisions. Then only you can propagate from one state to the other state. That is how Markov localization works. And again, discretization of this entire space also would require memory calculation, a lot of intensive memory calculations and computationally expensive as well. So this is basically true. Option A is basically a true statement, but we would require to select the false statements. So option A is true. We'll consider option B. Option B says Markov localization starts from any unknown position. Again, that is also true in case of Markov localization. So if the robot is at one position, and if you kidnap the robot, and if you put it in some other position, some other unknown position, Markov algorithm is also capable of starting localization from the new position also. Markov localization is also capable for solving this kidnapped robot problem. So that is also again a true statement. And option C states Markov localization recovery from ambiguous situation is not possible. So yeah, again, options B and C are basically opposite. So if we establish option B to be correct, then option C has to be false. In Markov localization, the recovery from ambiguous situation is not possible. So that is not true actually. Markov localization can recover from ambiguous situations. Or if we kidnap a robot from one location to another location, Markov localization is capable of localizing that robot at a different position also. Whereas Kalman filter localization is not capable. Kalman filter localization is not able to solve this kidnapped robot. It does not apply to Markov filter. So yeah, again, option C is false. And yeah, option D, it says Markov localization tracks the robot inherently very precise and efficient. Again, this is a given only for Kalman filter. It is not inherently very precise and efficient is not a keyword that could be associated with Markov localization. It is associated with Kalman localization. Again, option D is false. Right? So checking the answers, option C and D are the correct answers for this question. The question was to select false statements, and option C and D are basically false. These two statements only applies to Kalman filter. It does not apply to Markov filters. Yeah. So for question 8, it says for a robot moving in negative y direction in a global coordinate frame and which uses control inputs to predict position estimates. For such a robot, its position estimate will have option A, variance equal in x and y direction, least variance in the direction orthogonal to the motion, least variance in the direction of its motion. Variance will be greater in the y direction. So if we have a mobile robot like this, it says it will move in negative y direction. And how would the variance vary? If it only has odometry, if it only has control inputs to predict its position inputs, it does not have any sensors as of now. Any information regarding its sensors is not defined. This is x-axis and this is y-axis. How would the error vary? Initially, if we know the starting position of the robot, the error would be 0. But in what direction, as the robot moves along negative y-axis, in what direction the variance would be increasing? Whether it would increase equally in both x and y axes, whether it would increase in a direction orthogonal to its motion, that is x-axis, or least variance in the direction of its motion, that is along y-axis. Option D says variance will be greater in y direction. So what is the correct answer? So if you can recall, the variance propagation law is defined as sigma p dot. The variation of the new state, new update would be Jacobian matrix delta RL F sigma I hope you are familiar with this error propagation law, where yeah, the sigma, one second. So this term corresponds to the variance, current covariance matrix, current covariance. And this is the previous state's covariance. And this one, sigma delta, is the sensor's covariance matrix. And delta PF and yeah, this one. Sorry, this is delta. Delta RS, these are Jacobian matrix. So Jacobian, like this one would be delta PF would be dou F by dou X, dou F by dou Y, dou F by dou Z. and delta RLF would be dou F by dou SR dou F by dou SR. Jacobian, so this one corresponds to the Jacobian matrix corresponding to x, y, and theta. Sorry, this is theta, not Z. Jacobian matrix corresponding to x, y, and theta, and this one corresponds to the Jacobian matrix with respect to the left and right wheels. So this F is basically this vector x, y, z. Sorry, x, y, theta plus delta x, delta y, delta theta. So if you take the partial derivatives appropriately using the appropriate variables, if you take the partial derivative with respect to x, y, and theta, you would get this Jacobian matrix. And if you take the partial derivative with respect to the left and right wheels, you will get this Jacobian matrix. And this is the previous state covariance matrix, and this is the sensor covariance matrix. And sensor covariance matrix would be known to us. And the state covariance matrix, the covariance matrix of each of these states would be updated in a loop actually. So yeah, this would be basically updated. This would be fairly known. We would know this in advance. So for the initial time step, if we exactly know the starting position, if we know the initial condition of the robot at time t equal to 0, this entire covariance matrix would be 0. We would have these Jacobian matrices. This entire term would be 0, and this entire term would be non-zero. So that would be delta p prime for the first time step. And for the next time step, this becomes sigma p for the second time step. And again, it will get updated actually. It will get updated, it will get updated. So as time goes on, this value grows. This value grows actually. So initially we begin with the sigma p as 0. And as time progresses, with each update, sigma p prime will grow as time progresses. So the question asks, in what direction the errors will be growing? Is it along the direction of the motion, or is it along orthogonal to the direction of motion, or is it equal to both x and y directions? So again, this is a problem that can only be solved if you could only answer with some practical experience. If you simply run this command or this expression alone in a for loop, within a loop, just to simulate this error propagation just with odometry alone, you would see that the errors would propagate. This graph basically shows the robot to be moving along x-axis. And as the robot moves along x-axis, you could see that the errors are basically propagating. The major axis of the ellipse are aligned along y-axis, and the minor axis is aligned along x-axis. So the least variance, the question specifically asks, what is the correct option actually? In what direction you would have the least variance? So if the robot moves along x-axis, it will have least variance along x-axis or along its direction of motion. So this is a given fact. But in case of the other case, most variance would be orthogonal to the direction of motion. In this case, the maximal variance or the major axis of the robot is aligned orthogonal to the direction of motion. So this inference we can obtain from the error propagation law. This error propagation law. So with that inference, can we identify what is the right statement? Option A, variance is equal in both x and y directions. So that is not correct. Least variance in the direction orthogonal to the motion. Again, that is not correct. Least variance in the direction of its motion. That is correct. Variance will be greater in y direction. Again, this cannot be guaranteed because since the robot is moving in x direction, maximum variance in this particular case is along y direction. But if the robot is moving in a curved path, maximum variance will not always be orthogonal to the curve. But least variance would also always be tangential to the curve. So you can basically see if you define a trajectory, if you define an odometry, if you define some control inputs could be your delta SR and delta SM. So if you control this, you would get this value F matrix. And if you use this F matrix to derive the Jacobian matrices, and you would know sigma delta, the sensor covariance in advance, you can assume some value. And initially, sigma p would be 0. And if you use this formulation for error propagation, you can see the trend. Like however you define delta SL and delta SR, the robot will move accordingly. If delta SL and delta SR are equal, it will move in a straight line. Or if you want a differential action, you can actually have a differential action. So whatever be the case, you can see how this epsilon, the covariance matrix basically varies. So if you plot the major and minor axis of the covariance matrix, you can see how the variances in what all directions the variances would be. So in that context, the correct answer would be option C. Yeah, the least variance would be in the direction of this. Okay, question 9, choose the incorrect statement. So SLAM, simultaneous localization and mapping, is a process by which a mobile robot can build a map of its environment and at the same time use the map to deduce its location. So that is straightforward, true statement, because SLAM means simultaneous localization and mapping. And the statement itself says this fact explicitly. It says it's a process by which a mobile robot can build a map of its environment and at the same time use the map to deduce its localization. So mapping and deduce its localization. So simultaneous mapping and localization. That statement is indeed correct. And statement 2 states, in SLAM, both the trajectory of the platform and the location of all landmarks are estimated online without the need for any priori knowledge of the location. So again, that is also not correct. Both trajectory of the platform and location of all landmarks are estimated online, but we would require priori knowledge of the locations. So without that, we need to know the priori location of the robot. Then only we can identify or locate the landmarks. So we would require privacy again. So this statement is basically, sorry, I guess incorrect statements. So option B is also correct statement. Actually, we are dealing with SLAM. Actually. So simultaneous localization mapping, it doesn't require, I'm sorry, I made a mistake actually. It does not require any prior knowledge of its location. Because as the robot moves, it will create its own maps, and based on the new map, it will also localize itself. So first, the first objective would be to create the mapping. while simultaneously localizing the current position of the robot on the map itself. So yeah, option B is also a correct statement. Option C says SLAM stands for simple localization and mapping. So that is objectively a false. It says for simultaneous localization, not simple localization. And option D says in SLAM, only the trajectory of the platform is estimated online with the need of a priori knowledge of the location. So again, options B and D are opposite. So in case of a SLAM, we do not need any prior location of a robot actually. We would only require, it does not require any prior location. Does not require. So we have already estimated option B to be true. So option D being the exact opposite of option B would be false. Excuse me, yeah. So the question says to choose the incorrect statements. Not correct. So option C and D are the incorrect statements. Because in SLAM, we would only, we do not require any prior knowledge. We would only, the robot itself will create its map. It will map its landmarks while simultaneously localizing it. Yeah, so options C and D are false. And yeah, the question says to choose the incorrect statements. Yeah, moving on to question 10. Again, it deals with prediction estimate, prediction update of the robot. So choose the statement that best suits for prediction update. So option A says it estimates its current position based on previous position and odometric input. So is that correct? So that is correct, right? So if we have a previous position xt minus 1 and the new position xt. So yeah, just with the odometric control input ut, it would basically predict. So if this is the actual position, it does not mean that the robot will actually be at xt. So it would only, it estimates, excuse me, it's only an estimate of the current position, not this actual position. It's just an estimate of the current position based on previous position xt minus 1 and the odometric input alone. It does not have any, we are not bringing any sensor measurements as of now. So in that regard, option A is correct. Option B says predicts the current position based on previous position and sensor input. Again, that is not correct. Even that is not correct for perception update also. Perception update says the current position predicts current position based on updates current position based on the current estimate and sensor. That should be perception, and it does not even matter for prediction because in case of prediction, sensor does not come into picture at all. Option C says prediction predicts its current position based on previous position and previous uncertainty. Again, that is not correct at all. And option D states estimates its current position based on odometry and sensor input. So based on odometry UT and sensor input ZT, again, that is also not simply correct. So the only correct option would be option A. This is the only correct choice. Prediction estimates the current state xt if you know xt minus 1 the previous state and the odometric control input ut. That is all what prediction deals with. It does not deal with any other thing. Option A is the correct choice. So yeah, moving on to question 11. It says, given a differential drive robot which localizes itself in the work environment using the odometry based on wheel sensor, select the correct statement from the following. So yeah, so it deals with the localization of a mobile robot based on odometry and sensor readings. So we are required to choose the correct statements. The first statement says non-systematic errors can be eliminated by proper calibration of systems. So we have already discussed this in the first question, systematic and non-systematic. The other term would be deterministic, non-deterministic. These are also sometimes called random errors. And the systematic errors can be eliminated by proper calibration of the system. Can be a proper calibration, can be eliminated. Whereas in case of random errors, we cannot eliminate random errors completely. It could be due to external factors, environmental factors, factors that we have no control over. So in order to incorporate the effects or to compensate the effect of random errors, we would use some error models. We would use error models, you would define error models. So the first question says non-systematic odometric errors can be eliminated by proper calibration of the system. So that is simply not true. That is false. And the second statement says the drawback of using just the odometry for localization is that the errors are integrated, leaving no upper bounds for the errors. That is true. So if you are simply using odometry without using any, without comparing with the actual position or using sensors, if some errors are correct at some point, while integrating, it will basically grow without any upper limit. If you can see, as the robot moves in along one direction, so you have seen earlier, the errors would grow actually. And without perceiving or without using sensors to actually sense where the robot is, the error would keep on growing. So if you use some sensors, if you perceive, if you are using the perception update, we can bring down the errors actually using appropriate control inputs. And from there, it will again grow. And once it has reached some amount, we'll again use perception so that it come down. So without perception or without sensors, or in other words, just by using odometry alone, the error bounds cannot be kept in check. It will basically increase. So yeah, that is also a true statement, correct statement. Option C states non-deterministic errors are random errors. They have to be described by error models and will always lead to uncertain position estimates. That is true. All right, so I hope my audio visual is clear. I can sense some disconnection issues. All right, 1 second. Okay, please hang on 1 second. How is it now? How is my audio visual? Okay, thank you. Okay, the fourth option says variation of contact point of wheels, unequal wheel diameters are non-deterministic errors and cannot be eliminated. So again, we have already seen this in the previous question, I think in the first question. So variation of contact points of wheels. This is basically a random error. So no matter how perfect we make the wheels, or how perfectly we calibrate the system, we cannot ensure uniform point of contact of the wheels. So if the surface has some irregularities, it might lead to different traction actually. So if we want the robot to go straight, or the forces that should be acting on the ground should be uniform. But due to the uncertainties, like it cannot be just by the calibration of the wheels, just by making the wheels accurate, that cannot be ensured because that is also part of this environment. It cannot be ensured that the contact point of the wheels should be uniform throughout. So that is a random error. Whereas unequal wheel diameters, it can be made equal actually through proper calibration. Proper calibration. So again, this is a random error, and this is basically a unequal wheel diameters. This is a systematic error. The question says both are non-deterministic or non-systematic. So again, that is false. The only correct options are basically options B and C. So the question says to select the correct statements. Yeah, and the only correct statements are options B and C, or options 2 and 3 for that matter. Yeah, question 12 says belief state calculated before the new observation at T just after the control input is defined as. We have already covered this. This is the previous state xt minus 1. This is the current state xt. And if we are giving a control input, it would basically give you a belief state at the current position. So it says just before the new observation, just before. So we are not using the sensors yet, just after the control input. So what is that belief state called? Is it proprioceptive input? Proprioceptive means inputs that are internal to the system. Internal in the sense like odometers, sensors that are basically used as internal gyroscopes. Those comes under proprioceptive. Exteroceptive would mean inputs that comes external to the system, like ultrasonics or all this. Ultrasonics, maybe even, yeah, light sensors, vision CCDs and all this. And prediction update, is this correct? Just before the new, before the new observation and just after the control input. So that basically means prediction update. That is correct. And perception update comes after the observation, after the new observation. If we are updating the current state after the new observation, that is basically perception. And map does not even apply to this question. So the correct option is prediction update. So the belief state calculated before the new observation, but just after the controlling. So from previous state, just after the current input is what we call as the prediction update. Okay. So option 13, it says choose the wrong statements from the following. So the first statement says due to discrete representation of space grids, Markov localization is computationally expensive than Kalman filter localization. So we have already seen this earlier. Markov localization requires discretization of spaces as grids. So this is a correct statement. It's not an incorrect statement. And option B says Markov localization is capable of recovering from ambiguous situation. That is also correct. We have already discussed this in the previous question. So if we kidnap a robot from one location to an unknown another location, Markov localization can localize. Even if we kidnap from one position to another, it can localize with respect to the new position, new starting point. And option C says advantage of Kalman filter localization of Markov localization is that Kalman filter is more robust than Markov. So that is not correct, because Markov localization can recover from ambiguous situations, but Kalman filter cannot recover from ambiguous situations. If we kidnap a robot from one position to another position, Markov Kalman filter localization would basically fail. So that means it is not as robust, or it is not at all robust as Markov localization. And option 4 says Kalman filter localization models measurement noise as Gaussian distribution. Again, that is also correct. And Kalman filter localization is inherently more efficient than Markov localization. That is also correct. So inherently more efficient and computationally effective than Markov localization. These are mostly associated with Kalman filter localization. So the question says we need to choose the wrong statement. The only wrong statement is option 3. The Kalman filter is not robust than Markov's. It's not at all robust because it does not deal with the kidnapped robot. Yeah, a few more questions. A couple more questions. Arrange the following steps in the correct order for map-based localization. So option 1 says matching observations with map. Option 2 says observations with onboard sensors. Option 3 says estimation of the position update. Option 4 says prediction based in previous estimate and odometry. And option 5 says measurement prediction based on prediction of map. So if you can recall this slide, basically. So yeah, from the encoder, it'll get this it'll basically gives out this control input, odometric control input to the robot to first obtain a prediction actually. To obtain the prediction of the robot's next state, from the current state to the next state, it'll use encoder data to identify or to estimate the control input so that the robot would go to the next state. And similarly, from the other side, parallelly, the robot would make observations from the sensors. And yeah, and you also have map-based data. So data from the map basically says what the robot should see. Robot should see. And from the sensors, it says what the robot is currently seeing. Right. So based on the control input, the robot would move to a new location at time t. And based on the observation, the robot sees something, but with the map, we can see whether the robot is seeing what it should be seeing. It should be seeing actually. So yeah, based on this thing, what the robot is actually seeing compared to what the robot should be seeing, should be exactly seeing. So a matching between these two parameters would be taken care of. And the matched, and the corrected, if there is a difference, if there is a match, if there is a mismatch, then the control input would be updated so that the mismatch can be accommodated. Right. So if it is matching, then the new position estimate. So the previous prediction would be updated based on the map reading and the observation reading, so that the control input can be updated. Prediction of position. Yeah, it will be basically the right estimate of the new position. Yeah, so in that regard, the correct option would be option, yeah, the final option actually, option 6. So the right order would be, first, we deal with prediction actually. Prediction based on previous estimate and odometry. This would be previous estimate xt minus 1 and the current state xt. We would also have a control input ut, as I have mentioned. This is where we would begin first state. And the next state would be observation based on onboard sensors. Stage 1, prediction. Stage 2, observation. As we have raised here, stage 2 observation. Then we would see, we would compare that with the map, what the robot should be seeing, and the from the map, and from the sensors, what the robot is actually seeing. Then as option, then comes matching with the map actually. Number 3 would be matching the sense, what the robot is seeing and the what robot should be seeing, matching. Yeah. And the next statement would be measurement prediction based on prediction and map. Option 5 would be measurement prediction based on prediction and map. So since there is a mismatch, we initially predicted a position of a robot using control input, and with whatever information that is coming from observation and map, we will again predict the measurements, new measurements. And the final option would be estimation, position update. So whatever output is coming from this thing, whatever data is coming from, if there is a comparative difference between encoders, the encoder control input, and if there is a difference between observed data and map data, there's a difference, then we would give a new control input so that the tolerance can be, or the robot would actually move to the current position, exact position. So in that regard, the correct order would be 4, 2, 5, and 3. The first would be odometry, prediction using just odometry, and seconds would be observation using sensors. The third would be measurement prediction based on prediction and map, and the fourth would be matching observations, matching of the observations and map, and the final would be estimation. We would update the position using the updated control input. Yeah, and this is the final question. Dash is a process by which a mobile robot can build a map of an environment and at the same time use this map to deduce its localization. So is it perception? Is it localization? It is mapping. So again, as we have already discussed, the correct option is simultaneous localization and mapping. So it's a process by which it can build a map of the environment and at the same time it can deduce its localization. So both of these cover simultaneous localization. We check the answers, that is correct. And I guess that's it for today's session actually. And this basically covers some sample problems of week 5. And I suppose the deadline is also over. So I have also gone through some of the assignment questions of this year as well. So if you have any confusions, you can refer back to the lectures. right? So I hope it's fine, Murali.
Yes, it is.
Oh, okay. So that'll be the end of today's session.
Thank you then.
Thank you, Murali. Next week we'll deal with navigation, topics regarding navigation.
Yeah.
Thank you.
Thank you. Bye.
Bye.